Okay, tonight we're going to discuss what's referred to as time value of money. The discussion that I have here on these PowerPoint slides very much is um, covered in your textbook, and I encourage you to have a good understanding of it from that, in addition to what I'm giving you here. I'm going to kind of skip over some of these slides rather quickly because they only repeat material that is already contained in the text. This first slide discusses what time value of money is, and as long as you understand that, you should be in good shape. It doesn't have to do with the fact that there might be inflation going forward. It has very much to do with the idea that interest causes money to change in value. As you're probably well aware, if you have a savings account, interest is added to your account and your savings grows. If you owe money on a loan, you have a car loan or a mortgage or something like that, then you're also aware that interest represents a cost that you have to pay when you have loans such as that. The three main variables that are important with respect to interest are shown here, and they of course are tied together by the commonly known computation for interest, principal times rate times time. When we discuss the time value of money, we actually are referring to the concept that interest can earn interest on interest. Anyway, we talk about two different kinds of interest, simple interest and compound. In the simple interest case, interest is calculated, and by the way, interest rates are always stated on an annual basis. Interest is calculated using the formula that I mentioned, principal times rate times time, here where I refers to the rate. In this computation, this $10,000 would have earned $800 on an annual basis. If you were to have that money in a savings account and you withdrew the $800 at the end of the year, then during the next year, when you would earn 8% again, you would also earn another $800. And this is the concept of simple interest, that it involves an addition to interest but is calculated on the principal only. Okay, this slide also gets into an important issue, and that has to do with the concept of interest that is not calculated on an annual basis. So for instance, the example that's shown here demonstrates a borrowing that's only going to occur for 3 months. The interest rate, again, is always stated as annual. So the rate is 8% for 3 months. As you can see, the calculation then takes the annual rate of 8% and multiplies it by the portion of the year, 3/12, to get the amount of interest that would be due. Consequently, in settling this loan, Barstow would be required to pay $10,200 at the end of 3 months. So that's simple interest. Compound interest refers to the idea that not only can interest be calculated on principal, but it can also be calculated on interest. And there are many situations in business where this type of computation needs to be done. So this slide gives you a basic example of what the difference is between simple and compound interest. Basically, you can read this and follow it through. The left-hand panel rather shows the amount of interest that's generated on a simple basis. That would assume that that $900 does not receive interest going forward. So over 3 years, you get $900 a year. You have $2,700. If it's a compound interest calculation, then at the end of the first year, you have $10,900, and in the second year, you get interest on that amount as well. So interest has been added to the principal amount. The $900 that was earned was added to the interest amount, and then that was calculated, that was included in the interest calculation for the second year, which meant instead of not $900, you now are receiving $981. That's of course 9% on the principal of $10,000 and 9% on the $900 of interest that was earned. Your new balance at the end of the year is this, and in the third year, you can see what happens. This slide is here. You can read it. It gives you a more practical, perhaps, example of what it is that we've been talking about. All right, in this step, I'm going to begin to discuss calculations that we make in doing the present and future value, time value of money computations. Again, these are meant to be illustrative to you in addition to the material that's contained in the textbook. I do believe that what I presented you with here in these slides is a level of difficulty on par with, if not above, what's in the textbook. So hopefully you can use this as a means to better understand what's taking place. There are 4 tables that are contained in your textbook. They're in the appendix to chapter 6, and they are as listed here on the slide. In doing these types of problems, you don't have to use these tables, but you have to use something. Alternatives would be a calculator or Excel. The book does describe how to do these calculations in Excel, and I have no problem with you understanding it one way or the other. I am going to talk about it using the tables because I think conceptually tables are easy to understand. If you have an understanding of this on a mathematical basis, which is of course another alternative way to do the calculation, easy to do with a calculator or Excel as well, then you're certainly welcome to do that. These tables have as their components the items that you would have as inputs in your calculator or in an Excel file, an Excel worksheet, that would be used to solve the types of problems that are listed above of the 4 tables, as well as additional types of problems where you have unknowns of different types based on the different types of flows that are indicated. This is an excerpt from a table in a book. The book that I used to get these PowerPoint slides had tables that had decimals that go beyond the 2 decimal places that are in your textbooks tables. But you can understand that these are, in a sense, the same amounts. So this first discussion that we're going to have involves a determination of the future value of an amount when interest is compounded. This is the mathematical formulation to determine the future value of a current amount, and that is to take 1 plus the interest rate and raise it to the nth power, where n is the number of periods that are employed for the question that's at hand. Let me back up a second and show you this point here. Let me get to this. There's one point down here that I didn't mention earlier, and that is in these tables, you'll see on one axis the number of years on the left-hand column and the right-hand column, and across the top row you will see interest rates. Recall that interest rates are always stated on an annual basis. So the interest rates that you see at the top are only the annual rate if the compounding periods are 1 per year. If interest is compounded once per year, if interest is compounded annually, then the number of periods down the left or right-hand column of the table corresponds to the number of years. However, if interest is compounded more frequently, which is very often the case, then it's not the number of years, but rather the number of compounding periods. Put another way, if interest is compounded quarterly, if every 3 months interest is added to your savings account, then there are actually 4 compounding periods in a year. In order to adjust for this, the compounding period interest rate becomes the interest rate that's shown on the table divided by the number of compounding periods that occur in the year. In other words, if the interest rate is 16% and it's compounded quarterly, then that's 4% each of the 4 quarters of the year. And consequently, if you had a problem that asked you to determine the future value of an amount that was compounded quarterly with a 16% annual interest rate, you would, for 1 year, actually look at the intersection of the 4-period line and the 4% interest column, rather than the 16% for 1 period. You will get a different computation, as you'll see quickly, soon, if you compound more often. Okay, here's an example of this. Oh, I already did that. Yeah, this computation gives you the formula. Here's a further example of what I was just talking about with respect to the compounding periods. You can take a look at this. It will help explain what it was that I was just talking about. Okay, this slide demonstrates what can happen with a $10,000 investment based on the compounding period. The general rule, as you can see, is that the more frequent the compounding, the higher the amount of growth. Now, in order to check these numbers on the tables that you have, it's not possible for all those combinations because the tables don't contain interest rates at all the necessary amounts that are needed to do the computations. So, for instance, 10% quarterly would represent a 2.5% per quarter interest rate, and the tables don't have 2.5%. But they do have 8% and on an annual, semi-annual, quarterly, and perhaps even monthly basis. You can check those computations to see that the factors that are contained in the table would give you the same result as the amounts that are shown here. All right, in any time value of money problem, there are, as it says here, these fundamental variables. And in particular, what I want you to look at with respect to the chart that's shown here is that what we're talking about is a period of growth from some known or unknown present value, which, because of interest being compounded over a certain amount of time, it grows to some known or unknown future value. And in fact, any of these items can be an unknown as long as 3 of them are known. This computation, of course, looks very similar to the one I showed you earlier for the calculation of the future value of a single sum. The only difference is here it's referring to the factor from the table. That's what the FVF is here, the future value factor for n periods at I interest rate. So here's an example. This example is actually, I'm not sure why, I think the book, it's a small error here. They are showing you the computational method to arrive at the solution, which is perfectly acceptable. 1 plus the interest rate raised to the 5th power, this being a 5-year compounding annually at a rate of 11%. This is a pictorial depiction of what's taking place down here. And you can see that the arithmetic, 1.11 raised to the 5th power, is this number here. And that applied to the amount of the original present value says that the growth will become 84,253, that being the unknown future value in this problem. It says alternate calculation. The reality is this is just doing it with the table. So in the table, because this is 11% compounded annually, you're looking at the 11% column, you're looking at the 5-year period, and you come up with a factor of 1.68506. You'll recall that that was the 1.11 raised to the fifth power. So you get the same result. Of course, all this is subject to rounding error, this being 5 decimal places versus the 4, I said 2 earlier, but 4 that you have in your textbook. Another example of future value, take a look at this. This one has to do with the determination of the table, but the table and the formulas are interchangeable. Here's the table, here's the factor, here's the math, and there's the future value. This is the long way. It's not quite so long when you have something like Excel where you can copy a lot of cells, but the reality is that this shows the process by which that interest is compounded. Each period you're earning interest on interest, and consequently your growth is magnified beyond the amount that it would have if it was simple interest. All right, then we can take this one step further by seeing what the solution would be if the interest was compounded semi-annually. So in this case, you can read this 8% semi-annual, 3 years. The appropriate factor multiplied by the present value amount gives us 18,980, which of course you'll notice is greater than the amount that was received when the interest was compounded annually for 8%. This of course demonstrates the basic concept that the more compounding periods there are per year, the greater the future value will become. Okay, next we talk about the flip side of the future value problem, which is a present value problem. Here we're talking about what the value today is of an amount to be received or paid in the future. You'll see by this computation that shows here on this slide that the arithmetic is such that there's a factor, what we call the present value factor, which is multiplied by the future value amount to arrive at the current present value. You might also note that the factor that we use is the inverse of the future value factor that was used earlier. In terms of the table that we'll be using, the factor that we look up is contained in the table, and then this would be the arithmetic that you would do multiplying the future value by that factor amount to find the present value. So let's take a look at a problem here. Again, the pictorial depiction down here, the future value amount that's going to be received or paid in 5 years is a future amount, and the amount that's going to be equivalent to that in the present is what we're looking to determine. We know that the interest rate is 11%. We know the number of compounding periods is 5. We do the arithmetic. Again, this is the formula computation, not the factor so much. 1 divided by 1 plus the interest rate raised to the power of the number of periods involved gives us this number, 0.59345, and that multiplied by the 84,253 tells us that the present value of that amount is 50,000. Now, the implication of this is that if you can be certain of an 11% return for 5 years, you would essentially be indifferent between receiving $50,000 today or the $84,253 in the future. Here's the computation then next with the table. Again, it's the same problem. Now you're looking at the table that reveals the present value of a single dollar. When you look at that table in the 11% column, in the 5-period line, you see the factor here, 0.59345. And of course, that's what we had before, and consequently, the arithmetic is precisely the same. Here's another problem that deals with the present value of a future amount. in this case, we have interest at 12% compounded annually. The future amount they need in 4 years is $25,000. Because it's annual compounding, we're going to be looking in the present value of a single sum table, the 12% column, the 4-period line, and that will give us this factor, 0.63552, which then multiplied by the 25,000 gives us a present value of 15,888. If they were to put away that amount and get 12% compounded annually for 4 years, at the end of 4 years they would have $25,000. Now changing it slightly, what if it's going to be 12% but the interest is compounded quarterly? They still need the same 25,000 in 4 years, but now they get quarterly compounding. In this case, because it's a different number of periods than annual, we divide the interest rate by the number of compounding periods. So 12% divided by 4 gives us 3%. And we multiply the number of compounding periods by the number of periods per year. 4 times 4 would be 16. So now we're looking in the present value table at the 16-period line and the 3% column. The factor there, 0.62317, and that gives us a present value of 15,579. This demonstrates one of the important points, that when the interest is compounded more frequently, the present value is smaller than it would be if the interest was compounded on an annual basis. Here's another problem I pulled from another book. You can take a look at this. What amount do you need to invest today to get $20,000 in 5 years at 8% annually? And here's your solution. Okay, we can also obviously, as I indicated before, find unknown amounts other than the dollar amounts that we're looking for. So in this particular example, we know what the present value is, we know what the future value is, we know what the interest rate is. What we don't know is how long it will take to accumulate that future value that we're after. Again, pictorially it's shown down at the bottom here. In this case, if we take the arithmetic, if you'll see it up here, the future value 70,000, the present value 47,811, and we know that that multiplied by the future value factor, the present value multiplied by the future value factor will give us the future value. And therefore we can solve for that future value factor, dividing both sides by the 47,811, and we get a factor of 1.46410. Now what we want to do is we want to look for that factor in the future value of a single dollar table. And we're looking, because we know the interest rate is 10%, we're looking in the 10% column. And what we're looking for is a factor that is close to that number, such as this one, which is exactly what that number is. Should we have a factor that falls between two of these numbers, we can do interpolation to find out the solution. That's not something I'm going to have you being too concerned with. At any point, once we've discovered now what the factor is that would fit the equation that we have up here, then all we have to do is look across to see the number of periods, which is 4, to know that that's how long it will take for $47,811 to grow to $70,000 if the interest is 10% compounded annually. Here we are using the present value factors and doing the same thing. We know that the future value multiplied by the present value factor is the present value. If we solve for that factor, and again that's just the inverse of what the other factor was, it's 0.68301, and now again we're looking in the 10% column, and we again see that rate, that factor for 4 periods. So we again come up with the same solution. It'll take 4 periods to grow to $70,000. Here's an example of a problem where we're solving for the interest rate that we need. We know we need $1,409,870 in 5 years. We know we have $800,000 today. and we have 5 years to do it, we have to figure out what interest rate we need to get in order to generate that amount of money. So once again, using the same sort of arithmetic we did earlier, we've solved for the future value factor by dividing the future value by the present value. And because we know we're looking at a 5-period timeline, we're looking across the 5-period line to find a factor that is close to that number. And of course, the way the numbers have been worked out here, that factor does appear in the 12% column. Consequently, what it tells us is that it's going to take 12% for us to grow that amount to the $1.4 million that we need in the future. Here we are going the other way again, coming up with the same solution, but using the present value factor instead of the future value factor. Again, 5 periods will be the solution here. So you can see we can use either of the two approaches, either the present value factor or the future value factor, to determine these missing unknowns. Here's another problem that I pulled that you can work through. You can take a look at this at your convenience and see how it is that they arrived at the answer that's indicated there, answer C. All right, next we're going to shift gears a little bit and talk about what we call annuities. Annuities are a series of payments, referred to as rents, of equal amount. When you have an annuity, the assumption is that there is a fixed interval between the payments that's constant, and that interest is compounded once during each interval. This still allows us to account for the fact that we may have interest compounded more frequently than annually. An important concept down at the bottom of this slide is that there are two types of annuities, what's referred to as an ordinary annuity and an annuity due. With an ordinary annuity, the rents, the payments, or the receipts occur at the end of each period. And with an annuity due, the rents occur at the beginning of the period. The table that you have in your textbook is for the future value and present value of an ordinary annuity, not an annuity due. But I will show you how you can utilize the ordinary annuity table to determine what the solution is for an annuity due type of problem. So here's a conceptual presentation of what we're talking about. We have a series of $20,000 payments that are being made for 8 periods, beginning at the end of the first period and ending at the beginning of the 8th period. That's when the last $20,000 payment will be made. At the beginning of the 8th period, the end of the 7th period is what happens here. Because the first payment is made at the end of the first period, no interest accrues during the first period. Interest does accrue, however, after that, first on the $20,000, and then the interest is paid on the 20, and another $20,000 is added to the deposit, and then interest for the second year is calculated on the original $20,000, the interest that was earned in the first period, and the $20,000 that was put in at the beginning of the second period, the end of the first, which then will generate interest for another year going forward. So here's a simple problem, shows you how this can be determined. This is, again, sort of the long way of doing things. So what we see here is that at the end of period 1, $1 has been deposited, and it will earn interest for 4 periods, and that at the end of those 4 periods, which is the end of year 5, 4 full periods from the end of year 1, it's worth $1.57 because of the interest that's been earned at 12% and the compounding that's taken place. The interest, or the payment that comes in at the end of year 2 earns interest for 3 periods. This one for 2 periods. Whoops. This one for just 1 period. And of course, the payment that's made at the end of the 5th period has no opportunity yet to earn interest. So that if those deposits were made at that time and the interest rate of 12% was generated, at the end of 5 periods, you would have $6.35 that had been accumulated. Here's a computational depiction of the future value factor for an ordinary annuity. It is 1 plus the interest rate raised to the nth power, the number of compounding periods, minus 1. Basically what we're doing there is subtracting out that first period when there was no interest being earned. That divided by the interest rate gives you that future value factor. So you can plug that into your calculator if you want to solve these problems using your calculator. Here's an example using $5,000. We have five $5,000 being made, deposits being made at the end of each period, starting at the end of period 1. The interest rate is 12%, and the period is 5 years. So we're looking for what the future value of that amount is. We multiply the annual rent, $5,000, by 1 plus the interest rate raised to the number of compounding periods, minus 1. That divided by the interest rate gives us this factor. That should look somewhat familiar to you, 6.35, and therefore at the end of the 5th year we would have $31,764 accumulated in the account. Notice that there's only been $25,000 deposited. The other $6,764 is interest that's been generated on the earlier deposits and the interest that those deposits generated. Using the table, we're going to use this future value of an ordinary annuity table. We'll be looking in the 12% column and the 5-period line. Again, there's that factor. Multiply that by the amount of the deposits, and we get the same $31,764 we had before. Here's another type of problem, just to give you an example. This again is at 12%, $30,000 deposited at the end of each year for 8 years. What amount will be there after the last deposit? Here again, the table, we're 12%, we're at 8 years, and the factor is that, and so the future value of that $30,000 annual payment, remember this is an annuity, is some $368,991. Another example that you can work out. Take a look at that, and then here's the solution. You can read this when you get a chance. Maybe it would encourage you to be more serious about funding your retirement account. But it does show the power of compounding of interest. The other type of issue or problem that arises with respect to annuities is what's referred to as an annuity due. In an annuity due scenario, the interest, the first payment is made at the beginning of the period rather than at the end of the period. Consequently, the interest will accrue during the first period. As a result, as it says up here, the annuity due has one more interest period than the ordinary annuity. And consequently, we can utilize the earlier table that we have and determine what the annuity due amount is. The factor that we use when we have an annuity due can be determined by taking the future value factor of an ordinary annuity and multiplying that factor amount by 1 plus the interest rate, effectively picking up that first interest period that we otherwise hadn't accounted for. Here's a pictorial depiction using the table. At the top of this panel are the future value factors for an annuity of $1 at 12% for 5 periods, with the first payment occurring at the end of the first period. So of course no interest is accumulated here. When we have an annuity due situation, the initial amount goes in at the beginning of the period and consequently does earn interest for that first period. And you'll notice that the factor for the end of the first period adds 12% to the original amount. This is 1 plus the interest rate times this factor. 1 plus 0.12 times 1 gives us that. When we take this factor for period 2 and multiply that by 1.12, we're going to get 2.3744. So that's how these factors are all determined here. By multiplying each one of these by 1.12 gives us each one of these down here. You may also note that we can also do this arithmetic without multiplying by merely taking the factor for one advanced period on the ordinary annuity table and subtracting 1 from it. So effectively, this 2.12 minus 1 becomes 1.12, 3.374 becomes 2.374, and etc. And you'll notice how that's done. So either of these ways, either multiplying by 1 plus the interest rate or by subtracting 1 from the factor amount, will get us to where we want to be. Now we have some problems here, sample problems. So this first one, actually, it says future value of an annuity due, but they're actually talking about an ordinary annuity in this case. You want $14,000 in 5 years. You're going to make semi-annual deposits and get 8% compounded semi-annually. Consequently, this first payment is going to come at the end of the first period. This is an ordinary annuity. Because it's semi-annual compounding, you're going to divide the 8% by the number of compounding periods per year to get 4%, 8% divided by 2. And you're going to multiply the 5 years by 2 because there will be 10 compounding periods in that 5-year period. So for a 4% interest rate, compounded semi-annually for 10 periods, actually 8% semi-annually for 10 periods, you will find it in the 4% column in the 10-period line, and it is this factor here, the 12.00611. We'll show you that on the next slide. And the value of the rent, solving by dividing the 14,000 by the 12.006, is 6-month semi-annual payments of $1,166. Here you see the table amount with the ordinary annuity at 4% for that period of time, and the factor then is used in the arithmetic to arrive at the answer, much as we did before. Here's another ordinary annuity scenario, and this one we know what the future value is, we know what the goal is, we know how much we're going to deposit on an annual basis in this case with annual compounding at 8%. The question is, how many deposits will it take? So now, again, this is an ordinary annuity scenario, so that there's the first payment occurring at the end of the first period. What we're going to do is we're going to take the $117,332, the known future amount, divide it by the amount of the rents, and that will lead us to the future value factor that we'd have to multiply the annual rents by to arrive at that future value. Knowing that the interest rate that's available to us is 8%, we now go to this future value factor table. We look in the 8% column and we scan down until we find this factor, or obviously something very close to it. What we see there is that that factor is the future value of an ordinary annuity for 5 periods, and consequently it'll take 5 periods for us to generate the 5 periods paying $20,000 a year at 8% compounded annually will grow to $117,332. This is an example of an annuity due scenario where we have a payment going in at the beginning. He's going to make $2,500 payments every year for 30 years. They're going to earn 9%. We want to know how much will be in that account when he's finished. We go to the future value of an ordinary annuity table. We go to the 9% column and the 30-period line. And when we look there, we see the factor to be 136.30754. You'll recall that when we have an annuity due scenario, the way we convert that factor is to multiply it by 1 plus the interest rate. So we now have this as the factor for 30 periods, for a annuity due scenario, multiply that by the rents, and that gives us the 371,438. This 148.57522 is also the factor for the ordinary annuity for 31 periods at 9% with 1 subtracted from it. So that amount is not shown in the tables that you have in your book because it jumps from 30 to 35 without stopping at 31. But if you did see a 31 factor in there, you would see that it would be registered at 149.57522. Here's an example that involves an annuity due. We've got a deposit of $20,000 at the beginning of each year for 8 years with an annual interest rate of 12%. And the question is, what will be the future value of those deposits? Here again, we will use the future value of an ordinary annuity table and then either look one additional period and subtract 1 or multiply the factor for the 8-period annuity by the 1 plus the interest rate. And that's what's shown here from the annuity due, the ordinary annuity table. The factor, 12% 8 periods, is 12.29969. Multiplied by 1 plus the interest rate is this factor, and then we use that to determine what the future value of the annuity itself is. Again, and you can see this in your textbook if you look at the 12% column for 19 periods, for 9 periods, you'll find that the rate that shows there is 14.77, and consequently, if you subtract 1 from that, you end up with the 13.77 that we're using in this process. Okay, here's another problem you can work through. Again, an annuity due scenario. Again, use the future value of an ordinary annuity and adjust the factor either by multiplying by 1 plus the interest rate or subtracting 1 from the next period's factor. Here's the solution. All right, next, again, we're going to turn this around as we did with the single sum problems and talk about the present value of an annuity. When we talk about the present value of an annuity, again, it can be an ordinary annuity or an annuity due. First, we're going to discuss this from the perspective of the ordinary annuity, where the payments occur at the end of each individual period. So here's a pictorial depiction of this. Again, this is sort of the long way. What we do is we take each one of these annuity payments. We have 5 of them in this case at $1, and then determine the present value of each one of those. So using the present value table of a single sum, the present value of $1 to be received 1 year in the future is 89 cents. $1 to be received 2 years in the future, given the 12% rate, is 79.7 cents, and so forth. And if you add up all these individual present values, you get the present value of the annuity itself. So, put another way, this tells you that you would, if you can guarantee yourself a 12% return, you would be indifferent between receiving 5 $1 payments for 5 periods or receiving $3.60 today, because effectively you could take that $3.60, invest it at 12%, and you would be able to withdraw $1 at the end of each of those periods. And at the end of the 5th period, you would withdraw $1 and you would completely deplete the account balance that you had. Here's the computational process. The factor itself for the ordinary annuity is determined by taking 1 minus 1 divided by 1 plus the interest rate raised to the nth power, and then that whole amount divided by the interest rate itself. So in terms of plugging it into your calculator, this would be the formula you would use. Here then is a problem example showing the present value of 5 $6,000 receipts to be received at the end of each period with the rate 12%. We can use the formula. This actually just jumps right to the table amount. Looking at the 5-period line and the 12% column, this is annual compounding. We see a factor of 3.60478, and consequently the present value of that annuity is $21,629. Even though, again, notice the total amount that's being paid in is $30,000. We will always expect the present value to be less than the future value, whatever that may end up being. This is another example. This one is a common example that I use when I'm talking about this because it deals with the lottery question. You have an individual here who won $2 million in the state lottery, and much as is done in most states, certainly Ohio, $2 million means you win $100,000 for 20 years each. So that's how the total of $2 million comes up. If we assume an interest rate of 8%, the question is, how much has she actually won? What is the present value of the right to receive $100,000 at the end of each year for the next 20 years? Again, the present value of an ordinary annuity, you have that table with you. We know that the interest rate is considered to be 8% and the time period is 20. So the factor for the present value is 9.81815. And therefore, the present value of the annuity is close to $982,000. Here again, in effect, what we're saying is that you are indifferent, assuming that you can maintain an 8% interest rate. You are indifferent between receiving $1 million a year for the next 20 years or $981,815 today. Here's another example of an ordinary annuity with a withdrawal, interest compounded annually. How much do you need to invest today? What's the present value that will get you to allow you to withdraw that $10,000 at the end of each of the next 4 years? This is very similar to what I mentioned when I first started talking about these ordinary annuities for present values in terms of the ability to withdraw amounts based on the amount that's initially deposited. So here's a pictorial depiction of what we're doing. We need to determine, first of all, if we want to withdraw $10,000 at the end of period 1, what's the present value of that? What's the present value of the $10,000 we want to withdraw at the end of period 2 and 3 and 4? So here we see, again, the long way to do it. Take each one of those individual amounts and determine the present value of each one of them and then sum them to get the $31,699 that the present value comes up to. So if you were to invest that amount today and to be able to receive the interest that you're expected to get, you could withdraw $10,000 at the end of each of those 4 periods. And at the end of the 4th period, that $10,000 that you would withdraw would deplete the account balance down to 0. As it says, here's the more efficient computation. This 3.16986 is the amount that comes from the table, given the interest rate and the time period that's involved. Here's another example that you can read and work through. And here's the solution. Well, maybe that's the solution. Looks like the answer is B. They circled A. Here's another little sidebar. Take your time and read that, hopefully as a means of getting you to better understand what's going on with these annuities. And now we'll talk about the present value of an annuity due. Of course, an annuity due, just like with respect to future value, means the payment occurs at the beginning of the period instead of the end of the period. And just like it was with the future value scenario, we can equate the amounts that appear in the ordinary annuity table by merely adding 1 to the factors that appear in the table and you can see how that works here. The factor at the end of period 1 for an ordinary annuity is this amount. For an annuity due, the amount is that factor plus 1. And you see that to be the case in each of these various factors periods going forward. So now an example of the annuity due scenario. They're renting a satellite, 4 years annual payments, $4.8 million, the beginning of a year. If the rate's 11%, what's the present value of the obligations? We're going to find the present value of the annuity due factor, the present value of the ordinary annuity factor, multiply that by 1 plus the interest rate to arrive at the present value of an annuity due, and then use that to discount the periodic payments of $4.8 million. So again, looking at the table and adding 1 to the table amount is one way to arrive at this 3.44372. The other way is to multiply the ordinary annuity factor by 1 plus the interest rate. Let me back up here. I might point out that this is a very similar conceptually to a lease problem. You're paying $4.8 million 4 times to lease this asset. In this case, it happens to be a satellite. But the present value of those payments is only $16.5 million, even though the total amount that's being paid is about $17–18 million. The present value is the $16 million. This is the value that's assigned to the asset that's acquired in a lease scenario. And then the difference between that $16.5 million and the total amount of the payments essentially represents interest that's incurred in the leasing arrangement, interest on the borrowing that takes place to acquire a $16.5 million asset. All right, here we go back to the lottery scenario that we had earlier. Except in this case, she's going to get $100,000 at the beginning of the year, so it's an annuity due. We're still looking at 8%. This particular textbook had an annuity due table. You don't have an annuity due table. What you need to do is go to the present value of an ordinary annuity and then multiply the factor for 8% by 1 plus the interest rate. So in your table, what you can do is look up the present value of an annuity factor for 19 periods at the 8% rate. If you look that up, that number, 8%, 9 periods, 8%, 20 periods is, for 20 periods it's 9.81, but for 19 periods it's 9.6036. And of course, if you add 1 to that, you get the 10.6036 that we have here. So either way, add 1 to the 9.6036 that you see for 19 periods, or take the factor for 20 periods in the ordinary annuity table, which is that 9.81 that I alluded to, and then multiply that by 1.08, 1 plus the interest rate, to arrive at the 10.6036 factor that we're using here. So the present value of that annuity for her would be $1,060,000. Contrast that to the amount that we showed earlier. The reason that it's a little bit greater is that there's an extra interest period. She began to receive these payments at the beginning of the first period rather than at the end of the first period. Again, that's the distinction between an annuity due and an ordinary annuity. Here we have another example. Once again, you don't have the annuity due table, so in order to solve this, what you want to do is you want to look up the present value of an ordinary annuity at 6% for 4 periods. The factor at that intersection would then be multiplied by 1 plus the interest rate, in this case 6%, which would give you the 3.673, or conversely, what you can also do is look up the factor for 6%, 3 periods in the present value of an annuity table, ordinary annuity, and then add 1 to that factor. Either way will get you to the 3.67301 that you see here. Here's another example. This one deals with more frequent compounding. We have MasterCard balance of $528. You can pay off 12 equal monthly payments of $50. First payment is due 1 month from now, so this is an ordinary annuity. The question becomes, what rate of interest would you be paying? So again, using the computation here, looking at the total present value, which is this amount that you owe today, the rents, the annual payments, so monthly payments in this case be $50. The factor that we'd be looking at would be 10.575. And as it explains down here, using the present value of an ordinary annuity table, knowing that we've got 12 equal payments, and therefore we're looking on the 12 period row, you look across until you find this factor of 10.575. And you'll find that in the 2% column. Since that's 2% for a 1 month period, and therefore the nominal rate of interest is 24%, 2% each period. As it indicates, the actual effective rate is this 26.8%, which would effectively be the amount that would be charged if we were talking about a compound rate rather than a simple rate. Simple rate here is 24% per year. Here's another a problem you can look at. Take a minute to read this and make sure you know how to arrive at the solution that they came up to. This one deals with semi-annual compounding, so it gives you the opportunity to play around with the table in that fashion. Here's another example I pulled from another set of PowerPoint slides. This one asks you to determine what the annual payment would be that would have to be made if you're going to repay the loan in 4 years, and you're going to be charging or be charged 8%. So here we're looking at the present value, knowing what the total amount that was borrowed was, and then determining what the annuity amount is by dividing it by the present value factor given the 8% rate and the 4-period line, line that we're talking about. This last slide I just threw in to give you some examples of where we use some of the places we use time value concepts in accounting. Some of the most important parts are the first two, I think, notes and leases. Notes, that would be notes payable and notes receivable, because obviously those borrowings are going to occur with interest. I mentioned leases earlier. Leases are a very important means of financing your activities, but there is a cost involved with leases, and you can use these present value techniques to help understand what those costs are. You'll notice many of these other items frequently relate to assets and liabilities that stretch out over a long period of time. Those would typically be places where we'd want to take into account time value of money. Obviously, pension payments, you're working today, but I don't have to pay you your pension until you retire, yet I'm accumulating that liability as we go along. So I have to determine what the present value of that liability is to put it on my balance sheet. Long-term assets, same kind of thing. That somewhat relates to the lease question. That should be share-based compensation, not shared-based. Share-based compensation is payment in terms of stock, which again could stretch out over a period of time, and so on and so forth. The environmental liabilities also can extend over a period of time. One place where this concept would be used in a nonprofit setting would be where a donor makes a pledge to make a deposit, to make a contribution in the future, and perhaps make a series of contributions in the future. Once that pledge has been made, it's legally enforceable, and the entity can book the pledge as a receivable. But if the pledge is not going to be received for 10 years, then the value of the pledge is not the nominal amount that's going to be received in 10 years. We need to discount it, remove the interest component if we're going to book it in the current time period. All right, this concludes this lecture for time value of money concepts. Please work through the exercises, homework that I've assigned. Please, again, double check with what's in this video. Make sure you can work through the problems that I've explained to you here, similar to the ones that are in the textbook. As long as you can handle all those, you should be in good shape. All right, take care.